Very happy to have Chiara who will tell us about quantum corrections to Kerr thermodynamics.
Okay, thank you very much. So thank you very much for giving me the opportunity to speak here. Okay, today I'm gonna give you like some overview of some results that I got in collaboration with Dan Kapec, Sheta and Andy Strominger at Harvard, and also some work in progress, just a tiny bit of a flavor of what I'm doing with Mark Heidemann, who is also a postdoc at Harvard. So let me start. I didn't know which kind of audience was that, so I'm starting with some very basic introduction. So first of all, like why to study black hole thermodynamics? So black hole thermodynamics has been like known for more than 50 years. So it is something like it's not just an analogy between those of black hole mechanics and those of thermodynamics, but indeed it is like it's very much a driving force that drove like a lot of the progress in quantum gravity that teaches us very deep lessons. So indeed, according to general relativity, a black hole is a very simple object because there are no Kerr theorems under generic assumptions that say that indeed a black hole is characterized by very few quantities such as the mass of the black hole, its electromagnetic charge, and also the angular momentum. And indeed, so there are black hole like families of black hole solution which satisfy this law of mechanics here, where E is the energy or the mass of the black hole, K is the surface gravity, A is the event horizon, the charge, electromagnetic charge, and angular momentum, and the quantities which are conjugate to that, which is the electric potential and the angular velocity. So these are entire family of solutions satisfying this as a consequence to the Ansatz equation. But however, so this law here is very similar, like it bears a striking resemblance with the second law of thermodynamics, which reads exactly this. So and this led Bekenstein to indeed like tell us that indeed a black hole possesses an entropy which is proportional to the area of the event horizon here, and also like Hawking soon after discovered that by taking into account quantum effects, a black hole is not really black, but it radiates at a temperature which is proportional to the surface gravity. So indeed, like in particular, like as I was mentioning, a black hole is specified by very few parameters, and given these parameters, if you specify them, the solution is unique. However, if you compute this quantity, which is the black hole entropy, for instance, for the black hole which exists, which was observed like at the center of our galaxy, you get a really big number. Like number is huge, of the order of 10 to the 96. So this is like one of the fundamental puzzles that black hole posed, that indeed said that, okay, if you have just a unique solution from general relativity, what are these like very big entropy? What does it account for? So indeed, the entropy like provides us precious quantitative information about the degrees of freedom of quantum gravity. So quantum gravity is a theory which is needed to describe, for instance, the interior of the black hole, where the gravitational force is very strong.
In this temperature, I think that there is one over energy missing, unless this is a temperature of the horizon. This temperature does not depend on the mass, unless kappa is something.
Yeah, kappa is the surface gravity.
The surface gravity.
Yes.
Okay. So in terms of G Newton is.
In terms of G Newton, yeah, I will need to go back to it. So I think it's like 1 over m, I think, and then you will need to insert the slide. I didn't put it here. But okay, so like as I was mentioning, the fact that black holes have entropy is very and actually have huge entropy is very indicative of something, of some particular behavior of gravity. And the fact that entropy scales as the area, not the volume, is indicative of like some underlying like a feature of gravity, which indeed like some specific behavior of gravity, which is called holographic. So and indeed this led to the formulation of the holographic principle that says that indeed gravitational physics is encoded in a field theory in one dimension, much less, and this principle is embodied in the EDSSD correspondence, which states indeed that gravitational physics in the dimensional antimatter space is dual to a conformal field theory in one dimension. So we're going to make use of the holographic correspondence only towards the end of the talk. So for the moment, what I'm going to tell you in this talk, I will focus on some specific kind of black holes, which also have an which also have an ADS close to the horizon. But I will tell you a bit more about some specific kind of black holes because they're like as a simplified setup for our computations. And so indeed, I'll focus my talk on black holes which are extremal and near-extremal. So first of all, let me mention that indeed, once you have a black hole solution, the existence of horizon imposes some bound on the charges. So you cannot really, like for your black holes, if your black hole is rotating, you cannot lower the mass squared lower than the value of J, otherwise you have a Nickel singularity. And also in the case of a charged black hole, you cannot lower the mass below the absolute value of the charges. And if you have a black hole which rotates and also have electric charge, you have a band which is slightly more complicated, but it's of the same field. So an extremal black hole is a black hole which saturates the bound. So for our purposes, we are gonna focus on extremal black holes which are rotating. So extremal and near-extremal Kerr black holes. So for us, it will be saturation of this bound. So indeed, extremal black holes then have zero temperature. So saturates this bound. They are very particular solutions. They have zero temperature, and the black hole entropy is non-zero. It's finite, and it's also a very, very big number. So for this sort of configurations, the inner and the outer horizon coincide. So in this case, you have that indeed these objects have a huge degeneracy of ground states at zero temperature. And also, like in the case where you don't have supersymmetry, you also have, you don't have any symmetry protecting this huge degeneracy. And usually, like one can think that on including quantum corrections in the computation, maybe this non-zero, this huge ground state degeneracy might be lifted. And that's something that indeed happens according to our computation. Let me also mention that this specific scenario is something that might have some astrophysical relevance, because indeed simulations based on accretion disk for black holes show that indeed some astrophysical black holes could be nearly extremal, though some of these results were actually under debate. But just to give you an idea that it's a simplified scenario that could actually be useful in modeling black holes in our universe. That tells us something about black holes which could be in our universe. So for extremal configurations, also you have a very nice feature that you have a symmetry enhancement near the horizon, meaning that the geometry near the horizon develops an infinite smooth. So indeed, the region outside the horizon then seems to an observer just sitting on the horizon seem infinitely far away. And for instance, for static black holes, the horizon geometry is AS2 times S2. This also is a very generic feature that happens also in spaces, for instance, with cosmological constant. And in the case where you have a rotating black hole, you have that the AS2 is fibered on the coordinates over the S2, which is also pushed. So there is a puzzle for black holes near extremality that was pointed out by Preskill and collaborators already in the 90s. So indeed, let me just draw something here on the blackboard. So you have that. So here, so I'm just going to plot here in this diagram the energy available to the black hole close to extremality in function of temperature. So this is the energy. So indeed, this comes just from a simple semi-classical computation. You have that if you have a black hole which is close to extremality, the energy available to the system scales quadratically with the temperature. So it means that the energy available is a parabola. It is here. So this is the energy. Can you see it? Yeah, so write it here. Or not?
That's covered, but is it the same graph?
The same graph, yes. It's just that I'm gonna just write it down. So this is the energy available to the black hole, scales quadratically. So this is the parabola, the blue one. However, the typical energy of a Hawking quantum scales linearly with temperature. So it is a line which goes like this. This is the energy of a Hawking quantum.
What do you mean by the energy available?
The energy available, so it means that the difference between the energy, the mass of a black hole at temperature T, which is infinitesimal, versus the energy of the black hole, like the mass of the extreme black hole.
It's fixed.
So this will be
fixed J, right?
Yes, exactly. Fixed J. So this is like the energy available. I mean delta here, where the E0 is the one at the extreme above. So basically, you can see that from here. So at this temperature here, or also at this energy here, you have that the energy needed to emit a single Hawking quantum is more than the energy available to the black hole. So basically, you have that below this temperature here, the emission of a single Hawking quantum will take away all the energy available to the system.
Does it allows for J to change?
No. In this case, it's a fixed J. Just by lowering the mass, for instance.
But I mean, a typical
Hawking quantum might be a photon, or you could have angular momentum.
Yes, in this case, you just work at fixed J, for instance.
Will carry some angular momentum. The typical emission would carry also an angular momentum. So it doesn't need to have a fixed J.
In general, yeah, I mean, I think that in this case, you're working in an ensemble in which your system, like your radiation, like the angular momentum taken away from the radiation is negligible with respect to what you have, which is in general highly spinning because.
No, my question is that naively I could interpret this as below this temperature, the black hole would prefer to radiate with certain net spin.
Ah, okay. Yes, I think.
Instead of not being able to radiate.
Okay. Yeah, could be also the body that in our framework would be like all the computation will be done in an ensemble in which you have fixed angular momentum. So we, in this case, we kind of do not allow the process that you are mentioning. So provided that the radiation is emitted by keeping the same angular momentum, you will have this kind of paradox, meaning that okay, once you reach this point here, you will not be able to emit a single Hawking quantum. Thereby, your emission of radiation will not be a semi-equilibrium process, or quasi-adiabatic process, because basically the things that you're emitting will carry away all the energy that you have in your system. And we can talk a bit more about these other situations. So under our assumption then means that we have, like in this case, a paradox that this was pointed out by Freskin and collaborator. And so what we want to do is to compute quantum corrections to the thermodynamics of Kerr black hole to see if this paradox is solved. And this is not just a spoiler alert, that you will find that indeed once you compute the quantum correction to the energy of the black hole, you will have that indeed the energy available to the black hole will just be a ball. I'm just reinserting all the various factors here. I was just a bit sloppy. But if you compute it, like if you manage to put also the correct factors, you have that the graph that you get is this one. So you have that indeed at this point, you will have that this energy available to the system is bigger than the energy of the Hawking quanta. Thereby, you can trust your thermodynamics all the way up to very close to T equals 0. So this is something that we will show in our indeed computations. And the fact that if you get this sort of corrections, also what you have as a byproduct is that indeed the apparent degeneracy that you would have at temperature equals 0, so the extreme Kerr solution, is actually lifted. So you don't have any more a ground state degeneracy, but actually the density of states vanishes for E equals 0. So it means that the degeneracy that you will have for the extreme Kerr solution is washed away once you have quantum corrections. So our procedure is correct.
For this first point, the curve now lies on top. Is there any reason why this needed to happen? It's convenient because you can just.
It's convenient. It doesn't need to happen. For instance, in the next slide, I will show you that, for instance, when you have supersymmetry, so you have kind of two ways of resolving this paradox. Let's say one is whether you allow this curve to be higher, or also to admit or to think that between here and here you have this sort of mass gap in which you don't have any global state.
I'm not seeing why. I mean, if you really had a system like that, it just wouldn't emit, any quanta at the temperature of the system, but it could emit quanta below the temperature of the system. Why is it essential that it must emit? It wouldn't be a black body spectrum, in other words, but that's.
Yeah, exactly. So you would need, so indeed, this kind of computation, indeed assumes that the black hole emits at a black body spectrum with a temperature which is proportional.
There are gray body factors anyway, so in what sense this is qualitatively different from just the presence of gray body factor?
We're just taking ordinary material. We had a colloquium yesterday about this actually. Silicon at low temperature, there's a band gap. It doesn't emit a black body spectrum at all if it's at a low enough temperature because it just doesn't have any degrees of freedom at that level. I mean, it's pretty standard at low temperatures. So I don't know why this would have to happen.
You mean that then black hole, you would emit like in this region here, instead of having this, you will have that the black hole will emit at a lower temperature with respect to what you will
Well,
use
just
from
one.
the standard Hawking formula, or something like that.
You're not really lower temperature. It won't emit a black body spectrum at all.
Ah,
It'll emit
okay,
something
okay.
else. But again, this is pretty normal. It's not something exotic.
Okay, so this falls outside our main, assumption. We assume that in this case, the black hole spectrum will be like a thermal black body spectrum all the way up to.
Even though there would definitely be gray body factors just due to the finite size of the body. We can't emit quanta that are. It will be hard for it to emit quanta whose wavelength is much larger than the horizon size, for instance, which happens in this limit because if it goes to zero and the horizon size is finite.
So you,
You already, even for Schwarzschild, well, yeah, even for, like it's, you can calculate gray body factors for Hawking emission, and you know it's not a black body spectrum exactly.
okay,
So I'm just confused why that so seriously that it would be a paradox. It just seems like there's corrections.
let's see. Yeah, I mean, like, I think that in any case, what you will, you would like to trust your thermodynamics all the way up to temperature equals 0, right? In another, and this is like the simplest explanation why this should happen if you don't have, right? Without assuming any other gray body factor. We can discuss it later. In this scenario here, we don't take into account like gray body factors or some other thing. We are just explaining something like some, let's say, like this classical behavior, like this kind of classical paradox here, by taking into account logarithmic corrections to the entropy and to sort of quantum correction to the near-extremal particle. This is our working assumption, and if you want, we can discuss it later.
Okay.
So for
Last one, I'm
Yeah,
sorry.
yeah.
It's- Sorry, it's fine.
yeah,
What controls the slope of the red line, which is your
Yes.
quantum correction, will be the pre-coefficient, the
yes,
floral factor that accompanies the logarithmic term, right?
exactly, yes.
But what controls the difference between the blue and the pink, or whatever line? This is the previous one. So
Yeah.
here there is a competition between two. No, the red is going up to the
Yes,
above
exactly.
the other one.
Because
So, but it seems to me that there are two different parameters controlling. How is it possible? It's always above the pink.
it's always, you will have like, this is the quantum, like the part related to the quantum correction is this part here. This part. Which is always like, it's a universal log t to the, what we find is
And
like
it's always
universal
above.
log to the 3/2, yes.
Okay.
Log to the 3/2 factor that will always make it to go higher with respect to the line population of the protein.
So it means that the separation between the pink one and the blue one is also G dependent. Newton
Yes,
constant dependent.
Yes, I think so.
Okay.
Because like inside the mass graph, you will have. I will show you probably later, but yes, they indeed have also Newton constant. Okay, we can discuss more about this later, because they're very important points. So our working assumption is that we are gonna resolve this paradox that arise just at the level of this semi-classical interpretation by adding quantum corrections to the gravitational, by computing the quantum correction to the gravitational.
But in what sense this is a paradox? Because like the black hole having temperature, one physical way to say what it means, if you put it in a thermal bus at the same temperature, then the system is in equilibrium, right? So this paradox, does it contradict that statement? It's just not clear to me.
So what I'm saying is that here I will have that if I have to if you pull down a black hole and will just emit energy and so on, there will be a point here at which the black hole will not be able to emit on one single field, because the energy that will have will be over with respect to.
But that's the average temperature of the quantum. It would emit something that's in the table distribution.
Yes, exactly. So there is an assumption that, the fact this comes from the Planck distribution, and also this comes from the fact that, yes, there are also further assumptions into taking this. For instance, in order to get this, you will need to actually Yes, and for instance, have a low frequency gravity, low frequency photons and so on. So, yes, there are more assumptions to, like, yeah, for instance, the fact that you will for this, you're imposing that the frequency is low. Okay. Other questions? Okay, so assume that this working assumption work all the way up to here. Our paradox will be resolved by computing the corrected expression for the energy which is available to the black hole. And as I was mentioning, this will mean that if you have a scenario of this here, the correction for the Kerr black hole, which indeed does not preserve any SUSY, will lead to the prediction that indeed like you don't have any ground state degeneracy when you don't have supersymmetry, so your density of states will go to zero when delta E or delta M goes to zero. The thing will be different when you will have a black hole with charge and in particular with supersymmetry. At that point, you will have a mass gap, so it means that you will not have any state in this sort of interval, but you will only have a delta function. Like this delta function of states will be the one corresponding to the supersymmetry zero temperature black hole, but in which you have a mass gap, and then the density of states becomes non-zero again after this.
Sorry, concerning this point, because the area of extremal black hole is still large, right?
The area of the extremal black hole, yes, will
even with this quantum correction.
With this quantum correction, you will have a prefactor to the macroscopic area of the black hole that will go to zero when temperature goes to zero.
So I'm saying because of this quantum correction, the area of extremal black hole goes to zero?
Yes, as computed as a partition function of the near-extremal geometry.
Okay.
That's why, I mean, this particular correction will wash away the ground state degeneracy. I can
But
show you
is it in the regime? Because that sounds like a very large effect. So is it in the regime when this quantum correction can be trusted?
In general, they can be trusted all the way up to closer to this one, because at this point, when you go to zero temperature, other contributions, for instance, work holes and other subgroups will come into play. I will, when I will show you the final formula, I will tell you also what's the regime of validity. So a similar conclusion were like indeed these people, like in particular Yesu, Triacius, collaborators on, they did this work, but not for rotating black holes, but for black holes which have charge, so static black holes. And indeed they found the same qualitative behavior once you have supersymmetry, once you don't have supersymmetry. Indeed, once you don't have supersymmetry protecting your ground state degeneracy, it seems that from the naive computations that I did here, which of course has some assumption, as you were pointed out, the rho, like the density of states, goes to zero once you have once you reach extremal, or very close to extremal. I can show you the formula like towards the end, and then I will tell you also which are the regime. So okay, so for the Kerr, so we are gonna work with the Kerr black hole, and also we are gonna work in 4 dimensions. And indeed, we will make use of the fact that indeed for this kind of configurations, you have a very long approach, and indeed, and this is such that basically your system, like close to the horizon, decouples from the faraway region, and our computation indeed assumes the fact that we have the relevant part of the Hilbert space for the black hole solution will reside near the horizon, and indeed this part of the Hilbert space indeed can be captured by the gravitational dynamics really on the throat geometry. So we are going to make use of the near horizon geometry. In particular, what we are going to do is that we're going to compute the gravitational path integral, and we are going to use a saddle point approximation, and our saddle point solution will be indeed the length. And we're going to also use like some boundary conditions, which are like they are fixed by specific examples. So in particular, we're going to work in an ensemble where we fix the angular momentum. So Sen carried out a lot of works in this regard. So there's a lot of like a nice review that you can look up. But in general, you'll see that indeed the leading contribution from the saddle point gives you exactly black hole entropy. So if you compute the gravitational path integral and on the saddle point, you actually reproduce the black hole entropy. And the first correction that you have comes indeed from integrating over the quantum fluctuations. So basically, you have to compute the one-loop determinant, and there are divergences in this one-loop determinant, which arise due to zero modes in the one-loop computation. Very schematically and very hand-waving, you have indeed, like you have to compute like your modes in the one-loop computation, and some of these modes will have eigenvalue 0. So basically, it will not be damped here. So you will need to perform integration on an infinite interval, and this means that you will have a divergence because you need to basically perform a bunch of Gaussian integral, and you will have divergence, a divergence of this kind. And these zero modes indeed will be responsible for lifting the degeneracy of these ground states. And this, I will mention it later, will have also some relation to the fact that the zero modes are related to the Schwarzschild mode that appear indeed in the near ES2 correspondence. So what will be our approach, since if you compute the path integral in the near horizon geometry for the extremal black hole, you have the zero modes, so you don't have to have the divergences. What we're going to do is that we're going to make use of the near-extremal configuration. So we're going to add to our solution a bit of temperature, and we're going to use this geometry as a regulator for these divergences. We're going to lift the zero modes, and then compute the quantum corrections, and then try to send t to 0, and you will see like the result that we'll get. So okay, I'm going to then outline then the computation if there are other questions instead. So this is our prescription. These are our working methods. We are not claiming that it's the only one, but we are going to just report on the results that we get via this prescription.
You do not get any divergences in the limit t goes to 0, or do you throw it to that? You don't get
No, you don't get. So if you regulate it via these near-extremal solutions, you get a finite result, and you can take t equals 0, and you will see that you will get the results that was mentioned. There will be also some range of validity of these formulas that I will show you later. So okay, let me just sketch at least a bit the computation. So we're gonna work, so we're gonna start with the Kerr black hole. So the Kerr black hole like represents a black hole with angular momentum, which in this case is like as J equals AM. So this is the value of the angular momentum. It has a ring-like singularity, which is closed by two horizons, which are this which lie at this coordinate here, and you can easily compute the temperature and the entropy of the black hole because you can compute the area and the surface gravity here. We're gonna, as I was mentioning, we're gonna deal with extremal solution and with near-extremal solutions. And in this case, extremality is obtained by setting m squared equals j, and at extremality, the two horizons coincide, and also the temperature vanish. And classically, the entropy is 0. And you can also expand, so if you expand the mass and the entropy close to extremality, like you can verify indeed that the mass delta m like goes quadratically with temperature, and also the entropy instead goes linearly with temperature. And you can redefine, like you can rewrite this to expression in terms of a quantity which is called the mass gap, which is here. So indeed, if you want to go, like we're gonna use our near horizon geometry. So what we're gonna do with it is that we're gonna define a change of coordinates, like a diffeomorphism, which is a change of coordinates, which reads this way. We're gonna redefine the time and also our new redefined radial coordinate with theta, and then we're gonna have the usual angular coordinates phi and also theta. And we introduce a parameter epsilon, which we take to be very small. We keep it to 0. Which is proportional to, we send it to 0, which is proportional to the temperature. So we send to 0 the temperature. What you will get a metric which is called the NEC. So the near horizon extremal Kerr geometry, which is this one, which will be indeed the throat solution that I was talking to you about. So you see, this is nothing else other than ES2 at the space, and then, but it's not trivially fibered over the angular coordinates. So this geometry here has a particular, as a symmetry enhancement, as I was mentioned before. When you have an extremal solution, you have further symmetries. In particular, you have this sort of generators. You have generators of SL2R times U1. And just to recap, it has a maximum spin allowed for the black hole. It is actually a solution, a full solution to the Einstein's equation. So it solves the Einstein's equation at the level of this near horizon geometry is a complete solution. And again, if you're familiar with it, it's very important for the Kerr response. I'm not gonna delve too much into it. So what we're gonna do is that we're gonna compute the gravitational path integral on this solution. Here we're gonna compute quantum corrections. So first of all, we analytically continue to Euclidean signature. Then we're gonna send t to minus I tau, and regularity at zero radio coordinate eta equals 0 requires the fact that tau should be periodic up to pi. Moreover, then we're gonna compute the partition function in the near horizon region, and we're gonna integrate then over matrix subject to some specific boundary conditions. This boundary term will be just a Gibbons-Otto term. So the neck solution, the neck is a saddle point solution, and then we're gonna indeed write the general metric as the neck geometry. So this is G bar, the background solution, plus some fluctuation. And so in order to compute the correction to this path integral, we're gonna expand the action at quadratic order, and we're gonna have the contribution from indeed saddle point. Also, we're gonna have the contribution from this operator here, where D is a second order differential operator, and indeed the path integral computes then a functional determinant. Like very, very schematically. So we're gonna find out what is this D. Luckily, other people find it for us, like you can check it from some papers by silent collaborators. Indeed, what you do is, first of all, you impose a gauge fixing term, which is this one. And once you get this, you expand it at quadratic order, and you get your operator D that enters indeed into the one-loop determinant is this one. It's composed by these two box operators, various combination of box operators, and the Riemann tensor. Remember that HEP is indeed the fluctuation part of metric. So at this point, now one can see that indeed this operator here supports an infinite family of normalizable zero modes. So indeed, if you compute the operator that I was mentioning here, so if you plug in the neck metric in this one, you have the H mu that I can write down. All these functions here, they are annihilated by that operator. So it means that there are zero modes of your one loop development. All these modes, in these modes, n is an integer, n needs to be greater or equal than 1. So these are indeed metric perturbations which are left unfixed by the gauge condition. And indeed, you can find them as the derivative on the neck geometry of a vector, the derivative of the neck geometry of a vector psi n, which is this one. So basically, you can act as a derivative on the neck with this one, and you get this. So notice also that in general, you have that n.
So what is the superindex n? Is the order of what? Ah, the mode. It's just
mode,
h
yes.
supra n. Okay.
Yes, I indicated this. So n is the mode that appears, for instance, is the number that appears here, here, and here. Just notice that indeed we get these modes only for n, which is bigger than, like absolute value of n bigger than 1, because for n equals 0, 1, and minus 1, if you plug here n equals 0, minus 1, 1, you actually get exactly the generator that I was showing you before. These are exact isometries of the metric, so if you act with them with a derivative, like you take a derivative of the neck metric with respect to these vectors here, you get 0 because they are exact isometries.
But this is a finite dimensional group, and then later in the derivative you have an n, so you have infinite Killing vectors, right?
So let me just say that, so if you take n equals 0, minus 1, or 1, you get 0. So you don't get the zero mode. That's why the zero mode start from.
Oh, I understand. And the other values, n equal 2, 3, 4, 5. These are the asymptotic symmetries that live invariant the extension of SL2 cross C1.
They are not quite so. They are large diffeomorphisms that will have an action, like they will have an effect on this. There will be boundary time reparametrization. So
in other words, if you take the algebra of all these psi supra n.
Yes.
Do this generate a Virasoro, for example, or something?
Yes, I think so.
That's
okay. Yeah, exactly. So
These are exact isometries, or they're just a quadratic order?
No, they are not exact isometry. They will generate these modes here. They will change in it. But the effect that you will have is indeed the fact that so you can repackage this mode. You can take linear combination of these modes. You can define a function f of tau given this, then you see that the effect of these modes is basically a boundary time reparameterization. And if you're familiar with what happens for GT gravity, this would really correspond to the Schwarzenegger mode that you have in GT. So overall, so you have that this quadratic operator that appears in the one-loop determinant, admits this family, infinite family of normalizable zero modes. They are parameterized by elements of this plus 1 times step 2r, and indeed this creates some divergence in your one-loop path integral. So as I was mentioned here, the recap, so these are the modes. These modes cost no action and have infinite volume. So indeed you have a divergence in your one-loop approximation to the path integral. So you have that if you're staying in the t equals 0 solution, the path integral is divergent as it's not really well defined. You have this divergence. So you have to figure out what to do with these zero modes. So our strategy in this case is like following what these people have found in case of static black holes, is that we're gonna go one step further. Meaning we are gonna consider a geometry in which the temperature is raised infinitesimally. We called it not neck, like sort of thing, like it's a bit of a stupid name, but basically it's what you get by taking the subleading or like the first order in temperature in the decoupling limit. I'm gonna show you again. But basically we are gonna, so this sort of geometry couples, like is the geometry that you get when you couple, like it's the first order geometry that couples your near horizon theory, the near horizon region to the asymptotic space. And so we're gonna use this geometry here to compute in perturbation theory what's the correction to the eigenvalue for the zero modes. And then we're gonna see how these affect the one-loop determinants.
Before we do that,
Yeah.
are there negative modes of this operator?
No, in that case, no, we don't have we don't. So modes that you will get, I think in principle, no, actually I don't think I did that.
And the non-zero
At
mode?
least from the discrete spectrum of this, I think that's they start from the zeros.
And the non-zero modes, what's the gap?
You will need to, yeah, okay. Yeah, there are other zero modes that you can get. I think there are in some papers by Camporese Fucci.
Other zero modes?
No, they're non-zero.
Oh,
There are other. Yeah. I don't know. Yeah, I don't know precisely which one are. So for instance, if you tensor these modes that I showed you with some harmonic basis, with some higher spherical harmonics, then you will get modes which are higher than that. What was your question, sorry?
Well, just wondering what the gap is and how it compares to whatever you're going to find here after at this point.
Okay, I see. Yeah, that's a good question. I see. I don't know it on the top of my head, but I can for sure find out, even like as soon as I put that program paper. I know where to find it. I don't have it on the top of my head. But so okay, what we're gonna do is then, so we're gonna use this not neck quote-unquote geometry, so which for our purposes will be just obtained by indeed zooming in to near-iso geometry and take the first leading term in order t. So in this case, if you take only the leading term in this, like if you send t equals 0, you land on the neck geometry, so the extremal configuration, but then you have also like the first term here. That's what we take into consideration. It will be the first order something in T for this kind of decoupling. So the full correction for the metric, so this delta G mu that I showed you in the previous slides, is something ugly, something that Mathematica doesn't really like it, but you can actually still work with this metric here, something which is fully, you can compute it very easily. And this is part of your configuration, which we call not neck, with which you're gonna regulate our computation. So with this in mind, now we're gonna do like perturbation theory to compute the eigenvalue corrections. So for this case, like it's what you do in general in, for instance, mechanics. You will have this sort of operator here, where this is the leading order in T. You will have, these are the eigenfunctions. So these are the zero modes, where you can find also with this, I put the correction to the eigenfunctions, these zero modes. And this will be the correction also to the eigenvalues. For the zero modes, this lambda 0 are of course 0. And also again this one. So if you isolate the order, like the linear terms in temperature, you get an expression of this kind. And indeed, you see that if you are interested in only the correction to the eigenvalue, you actually don't need to know what are these, what's the correction to the eigenvectors. So you can just use orthonormality and you get the correction to the eigenvalue in this way. So this expression here, you need the corrected operator, d, and then the 0 modes that we had before. And the correction to the one loop determinant is easier, like it's very easy to find, which is like exactly, once you know the correction is delta n, these are 0, and thereby this will be the correction to your one loop determinant. So this will be the perturbation, like the computation of perturbation theory. So you can, just for the sake of simplicity, you can divide your operator into the part with the box and the part with the Riemann tensor. They're very big operators. You plug into Mathematica, you need to wait a bit until you spit out the result. But basically, you have two different contributions upon integration of the angular variable and time variable. When you sum up all together, you have actually something very, very easy. So these are very, very big expressions. You have to wait Mathematica 3 or 4 hours. But actually, what they sum up to is this very simple expression here. So this is the correction for all the for each for the value of each 0 mode which are labeled indeed by n. So this of course is linear indeed for by construction because we took the indeed. So indeed, so the correction will be that we have to sum all of them, starting from n greater than 2, this one, and then we are going to use, so we have the log, we're going to, this is the sum that can be turned into a product, and we use the zeta function regularization to obtain the final result, which is this one. So it means that the variation in this log z is equal to 3/2 log t. And this is the result that we obtained, and also the same result was obtained by the group of Fangamani just a few days after us. So we use the same procedure. It's not an independent computation, meaning the procedure is actually the same, but at least we got the same result. Like its computations are really like seen to log.
And the coefficient is J dependent.
Sorry, the computation?
The overall factor, the coefficient is J dependent.
No, this is like just a particular, yeah, no, this is like a, the coefficient is just 3/2 log t.
Ah, okay. And then you have some additional time. Okay, so.
Yeah, it should be So basically, so if you take all these things and you put them all together, you have that indeed you compute the path integral in the linearized geometry for the black hole. So you compute, you get the log and so on. So the entropy becomes this one here. So you have an initial factor t to the 3/2, which are due to the log t, like 3/2 log t that you get from the correction. This is the classical result, e to the s0, the number of states, and also this also comes from this first, as I was mentioning before, that the first term that you get as correction classically is linearly in t. So this is like classical result, and then this is the quantum correction. Similarly, you have a factor t to the 3/2 in front of it. Let me mention also that this computation here was also performed for charged black holes, and it also gives a very similar result. So indeed, with the t to the 3/2 in front of it. So a few remarks is this. So a few remarks that I'm mentioning is that indeed, so first of all, the approximation is not quite valid if t is very, very low. So it's lower than e to the -0, because basically you have that this term here will compete with this one. So at this point, below this temperature, indeed the partition function is very, very small. You can have other contributions, for instance, what we have seen from JT gravity so on. You have contributions, for instance, from wormholes and other non-perturbative contributions, for instance, so you cannot trust your approximation when t is super, super small, but also you cannot trust your approximation when t is very large, because indeed, if you have, so at this point here, when t starts being of order j to the -1/2, this term here, like this term here, will be comparable to this. So in this case, the correction term will become as large as the Mach metric. So you have this kind of upper and lower bound for this quote-unquote principle.
What do you mean when you say t to the 3/2 is order e to the -s? One has dimensions and one doesn't, right? So You're really comparing that to some other temperature to the 3 halves or something.
I will need to reinstate, yeah, I will need to reinstate all the units. It was a bit sloppy that.
Right. I mean, I guess what you mean is really that you just have to compute the action for some other saddle, including the prefactor.
Yes,
and then compare that.
exactly, when you are at fuel temperature.
But having not done that, or have you done that? Because if you haven't done it, then you don't really know where.
No, we didn't do that yet.
So that's some kind of lower limit on T, and there's,
Yes.
there's some upper limit on T probably as well.
Exactly, that's what I
the
said
next
here.
thing, yeah.
This is the lower limit and this is the upper limit.
Are you sure there's any region in between? Because if you haven't really computed the lower limit, then how do you know it's not?
Okay, so you're questioning this lower limit.
Yeah, well, I'm just saying, yeah, you don't actually know where it is, it sounds like, so could it be that it's actually about the upper limit?
Okay, I think that we have computed and there is a range of validity in which there is space between these.
So you found what you think is the next leading saddle?
We didn't find it, so just if you compute the lower limit via this thing, then you have that between this and this there is a range.
But how do you know where the lower limit is if you don't know what the action of the next leading saddle is?
No, we don't know what's the action of the next leading saddle. We just took this one for the temperature at which new saddles are the ones.
So, but my understanding is that the first limit is simply when one loop corrections become of the same order as the leading effect.
Exactly.
You know that the perturbative expansion may break down because you have 0 loop versus 1 loop that compete in the same order.
So our
Zero's dimensional unit is biggest.
I mean, and Planck equal 1.
But the units here are really not M Planck. I think the relevant units here are T compared to the sort of naive temperature scale of the black hole, which is 1/GM, right? So black hole's cold and close to extremality when T is much, much less than 1/GM here, which is what you're taking. But you're saying that GM times T all to the 3 halves has to be bigger than e to the minus S naught, which is non-perturbatively suppressed in GU.
okay,
So no, I'm saying just saying the relevant units are not Planck units. The relevant units here are compared to our Schwarzschild, right?
yes, I mean this one would be dictated by the Kerr.
Yeah. So I'm just saying T is being compared to GM on the left-hand side of that low temperature.
That's certainly something you can do, but it's not obvious that that's necessarily where it's worked out. Because there could be some other saddle which has a relatively small action. I don't see how you know where it is.
How can we show that for a very small t, you have a certain saddle that makes the action to be almost 0?
So you're saying that this upper bound would not be exact, or like, or what do you mean? Like we're just telling that at this point, actually there could be some other saddle that would actually compete when you have a very small temperature.
To get back to Matt's question, all I'm claiming is that the only scale this problem knows about is G
Size
times
of
M. It doesn't know about M Planck.
It's the size of the.
Yeah.
Other objections.
No, that's actually-
Of course,
It's related to what I was asking before. So this is a Euclidean calculation, but what does it tell us from Minkowski viewpoint? So you're not saying that as temperature goes to 0, the area of the horizon becomes 0. It's something.
if you believe these quantum corrections to the Euclidean path integral, then this is what. So we will have a quantity, like a thermodynamic quantity that, with quantum corrections, in this case, this Z black hole will compute indeed the black hole entropy will go to 0 when the temperature is very close to 0, provided that you stay within this
So
range.
is it? But from the Minkowski signature viewpoint, the statement is what you the Kerr black hole very close to its extremality, an observer who falls in will see
Well,
that.
it signals some sort of, that's like in a way that I mean, in a way, we already know that the Kerr solution is unstable due to, for instance, gradients and so on. So in a way, you can say that this tells you that a proper extremal Kerr black hole probably is not the object that you will find stable.
Well, but that's not a statement about proper extremal. We always work away from extremality. So,
I mean, if you trust this computation, like in this regime here, where you're allowed to take t small, not too small, but at least
well, this is
small, you
Euclidean.
will have that
This is Euclidean computation. I'm trying to ask
Yes.
what is the implication of this in kind of for actual black hole close to extremality. I jump there, I will see that the horizon becomes very small. Is it the statement, or or that's too naive?
Yeah, I think that how you would interpret this is just saying that it's a further kind of not proof, a further indication of the fact that an extremal, like an extremal horizon, extremal black hole is something that actually should not exist.
But you use the metric of the extremal black hole to derive this in the first place, and that metric, the horizon size is large. So I don't see that it's self-consistently, this can't be indicating that the horizon is getting smaller.
Right.
Well, what we have used in this case, strictly speaking, is the near-extremal configuration.
Or is it
like
that
kind of close?
the quantum correction to Bekenstein formula becomes very large, and the horizon area doesn't calculate?
It must be that.
Yeah,
right?
exactly. So basically, the
So
entropy.
it's not the geometry changed a lot, but that's somehow.
The entropy of the states of the black hole would not be the ones that are you macroscopically would compute with the extremal area of the black hole.
Well, they just have a little bit of splitting or something. So I can probably interpret this.
Yeah, all the states that you have at zero temperature basically get near over the temperature. Like so if I get delta function as I was showing you before, I get the function of t equals 0, they will just be smeared towards all this like toward the axis where you have temperature. At least that's what that's what this computation points out. And similar computation in case of charged black holes by EAs due to reaction so on, they're qualitatively similar to this and they show the symmetry. In addition, for the Kerr solution, we also have this fact that you have superradians, so you kind of know that your extremal Kerr black hole should suffer some sort of instability. So we didn't touch anything with respect to superradians in our framework, but it's just something that we kind of knew already that the solution, like this classical solution, is unstable in some way. So,
But that's because you don't have massive fields here, right? So
for now, no, we didn't touch anything related to superradians. All I'm saying is that from your starting point, if you think about the extremal Kerr solution, you already know that there is some instability going on. So perhaps this is something like showing that it's shown by the fact that the entropy of the density of states actually goes to 0 when you go to temperature sufficiently close to 0.
And that superradian instability doesn't show up as a negative mode of the.
We're still something. So we are still trying to investigate. I'm gonna tell you a bit something about this later. What you would need, I mean, what we think we will need to do is like now we have computed, like performed the computation from the near horizon point of view, but superradians kind of couple it to the interpolation spacetime. So we will need to redo the computation that we have done here at the level of the full bulk geometry, which is something that we are doing. It's just very difficult. What you will have probably, you will show that you will have probably an imaginary part for your partition function. That's something that we still need to understand and still need to figure out. So for the moment, we didn't touch anything. We didn't incorporate anything related to superradians here. All I'm saying that he was probably.
Once you have that, then your states have a width, and then the splitting you're calculating, if it's smaller than that width.
Yes, because you will have basically unstable states. You will have a width like there will be resonances instead of having delta function.
Right, and if this lifting of the degeneracy that you're finding is within that width, I'm not sure.
Yeah, sure.
Right.
It's in one of my bullet points in the
Okay. Yeah.
in the conclusion. So yes, we didn't take that into account so far. with this, we have indeed discovered is that we have used the procedure like a well-defined for us, what we consider a well-defined procedure to regulate the zero modes that arise in computations. For instance, the zero modes arise in computation also for SEM, what computes logarithmic correction and matches them to string theory and so on. When you have supersymmetry, the zero modes are regulated in such a way that you don't have this TT3 half. But when you don't have SUSY, it seems that their contribution is quite drastic at the level of the density states, at the level of what you would call the entropy. So okay, so just okay, as I mentioned, yes, like the ground states are spread out like over the energy, like a temperature like interval above the vacuum. And so there are also some subtleties that time. So just to mention like some subtleties in our procedure is that so we have computed the zero so the eigenvalue corrections to these tensor zero modes, but there are also like some other zero modes which are related to further redundancy, to further symmetries or isometries in the matrix. If you have static black holes, indeed you have that sphere is just like a round sphere, so you will have isometries of these two. If you have a rotating black hole, instead you have a residually one, so it's like the isometries that you get by direction. And then with these papers, indeed give also the form for these vector zero modes, which are these ones. So they are just similar to the ones that we have, but indeed they have a different refactor. And these are zero modes, so it means that they are annihilated by the same operator dnec that I showed you before, in case where you have fixed angular velocity. For fixed angular momentum, you will need to add to your Lagrangian another boundary term, so these modes will not be zero modes anymore. So in this case, these zero modes are ensemble dependent. So if you compute the eigenvalue correction for these zero modes for the static configuration, so first of all you verify that they're zero modes, okay, they're there, and also if you compute the eigenvalue correction with a similar procedure, you also get linear dependence in M. If you sum up the two contributions, tensors and vector zero modes, you get basically 3 log t, like with some factors. So you can compute this in the static case, but in the rotating case, actually, the naive guess that was given by Sen about this residual U1 symmetry, like it should be of this form here, and we have verified that this does not satisfy the gauge condition. So if you compute the zero mode that will arise from this particular vector here, you will have that the gauge condition is not satisfied. So actually, this is not a zero mode for your. It is not a zero mode, a vector zero mode for your dnec. And this was also noticed by the paper by the other people that also actually managed to prove, I think, under specific assumptions that there are no further zero modes. So this is still something like a bit of a puzzle that we have to solve. That indeed, so Sen predicted the existence of one further family of zero modes that, however, nor us nor these people also found. So okay, let me come now to the conclusion. So that the point is that these modes were ensemble dependent. So we have computed the universal correction from the test. So okay, so the conclusion is that according to our specific procedure, that may not be unique, but we have at least it's a prescription that we give at this point. We have computed the logarithmic corrections to the entropy of near-extremal and extremal Kerr, and we have found that there is indeed a 3/2 log t correction if you compute, if you regulate your zero modes with the near-extremal geometry. And the fact that you have this correction predicts the fact that the ground state degeneracy when you don't have supersymmetry is lifted. And of course, there are some open questions. As I was mentioning in the last slide, there is a rotational zero mode that indeed is something that we don't find and also other people don't find. We need to kind of see whether this is something that indeed one can construct, or maybe changing the gauge will lead to a different answer, something that we don't know. Of course, the fact that indeed we have taken a specific decoupling limit, we have taken a specific procedure, which is not really unique. So indeed, we will need to figure out, like, according to our procedure, we get a definite answer. We might get a similar answer or the same answer via some other procedure, or like our procedure is not unique, so we need to verify by some other way. It would be nice to verify it with some other kind of computation. What we will for sure need to do, like I think that we're working towards, is to reproduce this behavior from the full black hole geometry. That's what I was mentioning before, because this will help us to tackle also the superradiance, which is indeed a source of non-decoupling of the near horizon region with this vector sequence region. And of course, as I was mentioning in the previous slides, some work in progress also involves working with supersymmetric rotating black holes. So indeed, in this case, we need to put, a Kerr black hole in 4D cannot be supersymmetric because the extremality bound is not compatible with the biggest bound in unengaged reality. But if you work with theories in which you can have supersymmetry and extremality, for instance, black holes which are asymptotic by ADS, you can have supersymmetry. And so in this case, you can redo the same procedure and compute the quantum correct density of states. And you can actually see that there is a gap here between the first excited states, which is here, and the zero temperature solution here. Notice that this particular value of the entropy, you can reproduce this kind of entropy via localization computation in the 12 here. There is an extensive machinery to compute indeed all this to perform the microstate counting for the solution which has supersymmetry at the level of a dual field theory point of view. So we have computed this via a gravitational path integral, but it would be nice to see whether in this setup, we know that there are black holes in ADS, we know what's the dual field theory. It would be nice to retrieve this sort of correction at the level of the dual field theory. And probably, and hopefully, or at least in this scenario here, when you have black holes in ADS spacetime, you have hope to really do it because the dual field theory is pretty low. So, okay, this is the end. Thank you.
So you say that the coupling limit you take is not unique. You mean that instead of taking the neck limit, in which you accompany the rotation of the black hole as long as you get close to it, you could have taken this differently, or you mean that the next leading term, the one that is proportional to a temperature?
I can explain you a bit more in detail, let's say. So we can, let me go back. So what we have done, basically, we have taken the full geometry of a black hole which has temperature and so on, and we have performed this coordinate transformation here. And this gives you an expansion in terms of temperature. But you can also, for instance, start with the neck, like with the extremal solution, and then perform a decoupling limit. In that case, you usually define a parameter epsilon, which doesn't depend on temperature.
And that's a different result.
It gives you, we tried, I think it gives the same result. It's just that you will not see, so you will still have the lifting of the ground state degeneracy, that's for sure. I think that from what we have tried, I think you get a slightly different results for this one. But I think you will still be able to perform zeta function regularization to get a term of this kind.
The same 3/2.
Just that you will not be able to associate to this parameter epsilon the meaning of temperature.
Yeah.
Because in that,
instead of 2 pi and 0 t, you would have some epsilon that doesn't.
Exactly. So you would not know how to interpret that parameter at the level of black hole. So that's why we have opted for. I mean, this is for us. I think it's more like a more physical kind of interpretation. Just to start from the full Kerr solution and then do the decoupling limit in this way. But of course, many other people in places you see the lectures were compared. I think the decoupling limit is made directly from the extremal Kerr. So yes, indeed. So other kind of decoupling limit might be so they are available, and as far as we have checked, in one case, it more or less, I mean, with some caveats, it gives us results, but we are not confident at this point to say that it's always. So. And of course, yeah, our procedure is far from generic. We just gave one prescription, and we have stated what are our results, and that's what seems to happen. Then, of course, there might be other things actually in this result. Yeah, so
this might be a very naive question. So in the very last slide where you have Susie and then there's a mass gap, how should I understand this mass gap physically? And in terms of this paradox that you drew on the blackboard, does it solve that, or is the paradox still?
Yeah, I mean, the blackboard, it would mean that, it would basically mean that when you reach this sort of temperature here, you will not have any black hole state. See what I mean? Because basically this gap here in energy will be here. So there are two ways of solving the paradox, provided that you accept that the paradox is there in the first place. Either you see that in the no supersymmetric case, quantum correction take you all the way up to close by here, and they raise the energy available to the black hole above this one. Or you might think, okay, once you start hitting here, you have not any more black hole states, and then this part here is just not something that describes it. It's a very particular scenario, which is where you have black holes which are supersymmetric. So it's of course very idealized and so on. So that's what you would.
Thank you.